Welcome again to everyone. We are just resuming the mini course on Feynman diagrams. So, Helio, please. Just one
Oh,
more thing. One more thing. If you have any question, please, you can ask it by using the chat room. Okay? Thanks.
okay.
Please.
I think the best is if people just send an email with a question.
Okay, that works as well.
Okay, I'm going. Okay, if you see my screen, this is my email. So send your questions, comments, criticism to this email. Okay, it's much easier because I cannot see the chat room now, and at the end there is not much time. Okay, of course you can send a chat if you want, but I think send an email will be more efficient. Okay, so folks, yesterday we had a very complicated time because the connection went down a few times and they could not understand the connection was down. So we lost some time. Unfortunately, that's the way we have to do in this COVID time. So today I made some new arrangements. So I said yesterday the organizers tried to contact me once the connection dropped by sending me a message to WhatsApp. However, my cell phone was home and then it was connected to the internet and the internet went down. So I could not get a message. Today, my phone is not going through the Wi-Fi, going to the internet. So if there is a problem, the organizer send me a message. Okay, so yesterday we have a very, very short and very simple introduction where I had an idea of just showing some basics involving Feynman diagrams and how they relate to interaction. But what we really want to do is to be able to use some Feynman diagrams to make some calculation. So the best way to, and by the way, today I sent a message to the organizers, to Professor Castro Monte, with the suggested bibliography. Okay, so he will distribute. So what's going to do is to start the Feynman rule. Okay, so to make calculations from a Feynman diagram, you must follow some Feynman rules. A Feynman diagram is just a pictorial, just a picture that helps people to set up an equation and then calculate the equation. Okay, the best way for us to understand this is first work with a very simple, what we call a toy Feynman diagram. Okay, so let's have a toy diagram. Understand that although this diagram does not really represent any real interaction, any real process, the rules that apply to the toy diagram will be the same for quantum electrodynamics, for the quantum chromodynamics, or for the weak interaction. What changes is that the particles involved are different. The bosons, the exchange of the particles are also different. But in this toy diagram, we have a very simple case. Simple case. Okay? So, in this kind of thing, we have considered only interaction that involves only three kinds of particles, only three kinds of particles. And they call these particles A, B, and C. When you deal with the quantum electrodynamics, the parts will be electrons, muons, taus, or even quarks, whatever that has electric charge. In this model that you have, we call them A, B, and C. That's all we have in the C. And they have mass, MA, MB, and MC. So three particles, A, B, C, with mass MA, MB, and MC. And the antiparticle of A is the A itself, the antiparticle of B is B itself, and the antiparticle of C is C itself. So it's a very simple model, okay? And we're going to have that MA is bigger than MB plus MC, okay? The particle A has a mass that's bigger than the MB plus MC, okay? So in this kind of process, whatever, we're going to have what we call a primary vertex. If you remember from yesterday when I showed Feynman diagram, we show a process when we have, for instance, an electron, and at some point, we had something like that, an electron, for instance. This is for the quantum electrodynamics. Okay, so it was the basic vertex of quantum electrodynamic Feynman diagram. We have a particle, and at some point, this particle here will exchange a photon. Okay? Okay, in our toy Feynman diagram, what we have is something like that. Particle A, particle C, and then particle B. Oh, very simple. So we have a particle A, and at this point here, there was the sense what makes the particle B, and then particle A becomes particle C. Okay. Remember yesterday what we saw similar to that was when we were dealing with the weak interaction. With the weak interaction, when the particle exchanges a W, the W has electric charge, so the particle loses one unit of charge, or gets one unit of charge. So the particle will change. We can move from, say, from a quark D to quark U, for instance. Okay. From quark D to quark B, for instance. In this case here, the particle A, whatever it is, went to particle C by exchanging the B. So this is our basic vertex. So having this basic vertex, we can consider several interactions. For instance, we can have A decay. A decay is a process where the particle A decay in some particles, like this will be the following. We have here the particle A, and at this point, it becomes B and C. Okay? This is the lowest order diagram. Of course, as I mentioned yesterday, you may have many, many different diagrams. For instance, higher orders diagrams. For instance, we may have, let's now have, we may have, for instance, A, and here has C, and B, as well here, and then they exchange A, and have again B, and we have C. Okay? Or we may have something like this, A, and here we have a C, and a B, and then B and C. No, so at the end, everything we can see is this one. Okay? We don't see so inside, this is where we have the virtual particle. Okay, you only see what's outside. We only see outside. Okay, so we just see an A turning into a C and a B. We don't see what's happened inside. So maybe all that's happening is like in on the left. You have the A and just goes to B and C, and that's it. But maybe what you have is an A and goes to C and B, and then C and B exchange another A, and the end you have a B and C. So we see the same thing. A going to B and C. However, the process inside of here inside is the process. This is the process. Okay, we don't see the process. We do not know what's happening inside. What it means for all practical purpose is that all these possibilities contribute to the process. So in principle, you should be able to calculate all the Feynman diagrams. Another Feynman diagram that's possible is, for instance, say something like that. Have the A, and then the A goes to B, and here we have a loop, A and B, and then go again to B, and here we have C. Okay, if this looks strange to us, well, that's okay. Remember that we said at some point that the intensity of the Feynman diagram, each Feynman diagram will produce a number that we use for calculation. And as more vertex are present in the Feynman diagram, smaller the contribution, because each vertex will be connected to the intensity of the interaction itself. So if that intensity, that constant, is smaller than 1, and it is smaller than 1, then what happens is that as more vectors we have, smaller and smaller the process has. There's something similar to what happens when we have, say, a series, like a Taylor series, when you have terms that go to x squared, x to the third, x to the fourth, the fifth. So to really calculate the series would be, we have to calculate all the terms. However, we know that as the order of the term gets higher and higher, less and less relevant the term is. So at the end, we can work only with a few terms. But to be precise, we need all of them. So you can understand this way. So each Feynman diagram is a term of a series that put together represents the process. So, and if now see here, this first person, the lower cell diagram has only one vertex. Here in the center, we have diagrams with 3 vertex. See, both have 3 vertex, 1, 2, 3. Here we have diagram with 3 vertex. And so I can write an infinite number of Feynman diagrams. Most of the times, I said only this one will be relevant for the process. Okay. Now let's see now how to be a third order diagram. Say third order diagram. For instance, we may have it like this. Let's see the process. Okay, so this was the process A going to B. So this will be A going to B plus C. There's a decay. Particle A going to B and C. Okay? A decay. Now, I may have also a process that shows the interactions between 2 particles. For instance, A plus B going to A plus B. That's what is called scattering. So what you have here is the following. Particle A interacts with B, B, producing A and B. So this process could be represented by the following Feynman diagram. We have the particle A, we have the particle B. So here at some point they interact, and then we have particles, say, A and B. Okay? Or we may also have A and B. You see, here we have A and B. Okay? So all this A plus B go into A plus B. So we have two Feynman diagrams, and they are not exactly the same thing. Okay? Here, A and B exchange something, in case it exchanges C, for instance. And then we have A and B. Again, only thing that we see, and we can see, is here. We only see A and B entering the system, and A and B leaving the system. Here we see A and B entering, and A and B leaving. So, but what happens inside is different. And in the second case, once we have A and B, they get together, they turn themselves into C, and then the C sometime later goes in A and B. So to make a calculation of this process, should be able to calculate both processes or any others that we are able to represent. Another example will be, for instance, the process A plus A going into B plus B. What you have here is, for instance, a particle A and another particle A, both interact B, and then we have B and B. Okay? Remember this Feynman diagrams, usually what they mean is that here we have time. We mentioned that yesterday. Okay? And this diagrams, they show the process. It doesn't mean that the particle A is moving to the right or to the left or whatever. It just means that two particles, A and B, they interact, because again, what we see is, this is the process, okay? As I mentioned before, this is the process. The process is here. Okay, and this process, that's what we have here. Okay, so, but how can we calculate this? So each one of these Feynman diagrams is going to have one number. That number that you calculation. For quantum chromodynamics or dynamics of weak interaction. I have to repeat it. Difference would be that rather than have A, B, and C, one electron, muon, taus, and neutrinos, and the interaction, you have photons, you have Ws, of course, it's more complicated, and this pointer here is going to show the interaction happens. So they will exchange not a C, they will exchange a photon or a W. So, and the interaction is different. As I mentioned, the strong interaction is much higher intensity than the electromagnetic. The electromagnetic is much more than the weak interaction. So although we may come with diagrams that topologically are the same, they have the same topology from electromagnetism and for weak interaction, they may look the same. However, the intensity of the interaction, so what happens here in the vertex, this is the vertex. The vertex is where shows the interaction happening. So if we have two diagrams, one has the vertex is the strong interaction, so it's exchanging a gluon. The other vertex is electromagnetic, it's exchanging a photon. The one exchanging a gluon is much more intense, you count more to more. So, but let's see, that now we have a recipe, how to process this. Now, oops. Now, how to calculate this? The amplitude. Oops. How to calculate it? So, for that, we have to follow a set of rules. And that's what we call the Feynman rules. There will be the Feynman rules for quantum electrodynamics, the Feynman rules for electrodynamics quantum, the Feynman rules for the weak interaction, and then we have the Feynman rule for the STOI process. So let's write the Feynman rules, and then let's apply it to some model, okay? Let's start with what's the rule. First thing we do with the Feynman diagram. Oops. First thing is, well, we must know what's going in and out. Okay, which particles start going into the process and what comes out of the process. So you must have something like that. Okay, and we have particles getting into, and have particles leaving. Okay, here inside of the dotted area is where the process happens. That's where things happen. Things happen here. That's where the interaction happens. That's where electrons and the positons will exchange photons, for instance, or quarks will exchange gluons. Okay, so those are the parts entering, and they have so. Quasi-momentum, we all know what the momentum is. Momentum is just, each particle have a momentum that pretty much depends on its speed, but it also has the energy. So the quasi-momentum is a quantity. Later, if you have the opportunity to show something of relativity. So basically, quasi-momentum will be a kind of a vector, okay, that it has four components. One is the energy, and the other three components are the components of the momentum. So here we have to, for each particle, we're going to have, say, a P1, P2, and Pn. And leaving, we have, say, P4, P5, and Pn. Notice that the number of particles getting into the system does not have to be the same as the number of particles leaving the system. Okay? Maybe you have, as indicated, the first TOI diagram that show we have just one particle get into the system, the particle A, here. You have only one particle getting into the system, particle A, and they have two particles leaving, B and C. And the same is here, or here. So if you have, they don't have to be the same. In the second case, here you have two particles getting into the system and two particles leaving the system. Maybe you have more particles getting into the system than leaving. So it doesn't matter. Okay, we have to mark all the quasi-momentum of all the particles. Okay. Now, what happens that inside of the diagram, so the part that you don't see, you also have an exchange. So this diagram here, A exchange, the two particle A, C. So this C that was exchanged also carry momentum or quasi-momentum. Okay? Remember that no matter what you do, energy and momentum must be conserved. So if the particle A loses some momentum, the other particle must get that momentum. So at the end, the momentum at the beginning, the momentum at the end is the same. So here, right with another column, and register, we have also multi-register. Okay, that's what I do. But to make a difference, we call the internal momentum we call Q, and the external one we call P. Okay, so every time you have Q, we know that we're talking about what's happening inside, like what's going on to a photon that's exchanged, a W, or whatever. In the case here, for instance, what's the internal is C. So we have for A and B, we say, for instance, here we say you have P1, here we have P2, here we have P3, and here we have P4, and then here will be key 1. There is only one. Okay, that's what we have to do. Now, it's important. You have to draw an arrow in each line showing the direction. Well, this is totally okay. As if you find what is negative. Of course, for the same problem, you must use the same definition. But so once you have a Feynman diagram, you have particles getting in, particles getting out. You must define where is the positive direction and where is the negative direction. So this is the first thing you have. Giving a Feynman, identify what's getting into, what's getting out.
Helio?
Out on the then. Number 2. Hello? Yeah.
Yeah, it's okay.
Say, what's the problem?
It's
okay.
not fluid.
If there is a problem, just send a message to WhatsApp. Okay, now, number 2. Number 2. Now when things start getting messy at some point, because Feynman diagrams are pretty much named for weak interaction, electromagnetic interaction. You have a particle, the particle exchange something. Okay, so that vertex is where the interaction happens. So for each vector, so for each vertex, It's going to, an interaction happens there. So for each vector, you have to add one factor like that, minus I, G. And G is the coupling constant. So in the case of strong interaction, the G will be much higher than the case of quantum electrodynamics. In our case, our toy diagram, this just one could call it G. For instance, there's a message, WhatsApp and all the thing. Okay, so then what happens is that I got the message. Okay, and that's in this case here, for instance, this diagram, we have two vertices. Right? So for this case that has two vertices, we're going to have minus IG for one vertex and minus IG for the other vertex. What makes minus G2. Okay? Easy. In this case here, we also have two vertices. Two vertices. Here, two vertices. In this case here, we have one. So here will be minus IG. So notice that the diagram with two vertices, you have G squared. So if G is smaller than 1, G squared is smaller than G. And so on. If you have a diagram with 4 vectors, things get even smaller and smaller and more. Okay? So G basically defines the intensity. G defines the intensity. Okay? So now we go to the third step. Okay? Now, there is something that's exchanged here, right? See, in this diagram, the two particles, they exchange something. In the case, they exchange and C. This thing is exchange we call a propagator, because basically that's what's doing. It's propagating from one particle to the other particle. So we have a factor. Okay, for each Washington line.
Helio. Hello, Helio. Helio,
Okay,
can you
hello?
hear me? Yeah, there are a couple of questions here.
What? Yes, I can hear you.
Yeah, the first one is the G constant. Is the G constant a-dimensional?
Okay.
Did you hear me?
No.
Okay, I repeat it.
It depends on the interaction. It could be added. Yes, I hear. In this case here, no. It's G, yes, G is not does not have a dimension here. They just show the intensity of the interaction. For instance, it would be 0.5, 0.3, 0.2, 0.1. In this case of this model that you are doing here, we are just going to have the result with letters, not numbers. So when we work with the electromagnetism or quantum electrodynamics, then we have to know what's the value of G. And then at the end of all the calculation, then we replace G for whatever the value. And in the case here, there will be no value. A, B, and C, and G will just be numbered. Because the idea is to show how to work with a Feynman diagram. Then, when you go to a real one, like a QED, then we're going to have values. You're going to have momentum, real momentum is going to have real value for G. In the case of electromagnetism, the G will be 1 over 137. That's a constant that shows up very much. So it does not have a dimension here, because it just shows the intensity of the interaction.
Okay, there is another one here. Another question here. Is G related with the fine structure constant?
In the case of the quantum electrodynamics, yes.
Okay.
But in the other particles, for the other interactions, no. For the quantum electrodynamics, would be 1 over 137. All this, if you get to one of the books, or usually at the end of the book, or in some part of the book, they have a kind of a table of a few pages, 1, 2, or 3 pages, that list everything for each interaction. So they're going to have they're going to show there the fundamental Feynman diagram for electromagnetism. And then we have all the information about the G, and when there's for the chromoquantum dynamics, we have all the information, including for the gluon and for W and so on. Of course, there are some people in the world that probably know all these things by heart. But if you really want to do that, and we are not expert on that, we just go to the book and just look. They show what the values are for us to use. But whatever you do is the same. See, we are adding a factor here. M is the mass of the exchange. For instance, in the electromagnetic interaction, okay, they exchange a photon. The photon has no mass. The mass is 0. So in the case of the electromagnetism, the second term here, this term that is here, will be 0, because the photon does not have mass. However, if we're dealing with weak interaction, when they exchange a W or they exchange a Z, the W and the Z have mass. So they will show, the mass will show here. Okay? So it depends. So this is a very general term. In our case here, they exchange, for instance, here they are exchanging a C. Then the propagator here is a particle C, and in this point here, we're going to have the mass of the C. C squared is the speed of light, right? So we're going to do a full diagram, at least one full diagram for quantum electrodynamics. And then we're going to use all these things. And at some point, of course, at some point, we have to make some simplifications, okay? Notes that the situation we're going to you are having, say, electrons and the moons, and depending on the situation, you may consider that the mass of the electron is 0. By considering 0, you are saying, well, this mass is much smaller than all the other masses involved. We do that a lot when we solve a problem. Okay, we have two values. One is 3, the other one is 100. Well, we may just ignore the one that's 3, just to make our life easier. Okay. Okay, this is the propagator. And then what we have here, this Q, J, is the quadrimomentum. The question someone did was if it was related to the fine structure. Okay, remember that we're not talking only about the QED, quantum electrodynamics. We're talking about everything. So for the case of the quantum electrodynamics, well, that's true. But for the case of the strong interaction, that's not the case. Or for the weak interaction, that's not the case. So this is a very particular situation. So QJ here is just the quadrimomentum of the line. And the mg of the line And mj is the mass. So, as I mentioned, in this case here, Q is the quantum momentum that's exchanging here, and C is. Note what's happening here. The A and the two parts of A, they are exchanging they're exchanging energy and they are exchanging momentum. So the quantum momentum of A, the A at the top and the A at the bottom, they will change because one of them is sending something, so sending energy and momentum, and the other one is receiving energy and momentum. So this pretty much makes sure that the energy and momentum is conserved. This is one of the points that you have to consider now. Okay, this was number 3, okay? Now, number 4. For each vertex, write 2, 3, 4. So that a vertex, something like that. Huh? There are only 3 lines in a vertex. Okay, one line is say arriving in the vertex, the other 2 are leaving. So, since the momentum and energy must be conserved, so the energy one and the energy 2, and they have momentum and momentum. So this should be the same. So wherever energy is particle 1, say 2 and 3. Whatever energy particle 1 loses, let's say the energy here is 10. So the energy will have to be 7, 3, or whatever. The same goes for momentum, but remember that the momentum is a vector. Okay? And this has to be preserved. So what is this? Is the delta function. What is showing here? And let's see what is the K, né? K are the 3 okay. The arrow. Okay, so if the arrow is leaving, so in this case for 2 and 3 is leaving, we say that this K, the quantum momentum, this K is negative. It's just a convention that you did at some point. Of course, you could do everything in the order to be the same. So what this thing is here is going to follow K1 plus K2 plus K3. What's the delta function? Remember that the delta function, the simple term, is equal to 0 for x equals 0. On term, this means I x. Okay, so what happens here that this delta that we are adding to our equation is 0. If this value here does not suffer. we must have K1 plus K2 plus K3 equal to 0. What means that K1 is equal to minus. So conservation of momentum. Only when this condition is satisfied, we have the delta different than 0. Otherwise, the delta is 0. It means that the process cannot happen. Okay, just a way to guarantee that. Before someone asked about this 2p to the fourth, I should answer that I do not know. But many decades ago, in the 50s or so, a student asked Feynman himself about this 2 pi to the fourth, because at some point, you see that this will just disappear. And someone asked, well, if this disappears after all, why is needed? Just forget about it. Feynman almost had a stroke, okay? And said that this must be there, it must be there. So I believe that for some theoretical reason, there may be situations when this is important. But for our case, in fact, doesn't matter. But I have to be here just to make the presentation complete, okay? So what, just to reinforce this, so this term, okay, assures conservation of momentum and energy. Okay? So when you deal with a real problem, and they have to add the momentum and the energy, and then you must be sure that the energy is conserved, the momentum. If you draw a Feynman diagram that does not respect conservation of energy, conservation of momentum, this Feynman diagram does not represent any real process. Any process could happen. Okay. Number 5. Number 5. For each I want to say again that these rules will be pretty much the same for electrodynamics and quantum dynamics. Okay, what we change is the particles that are exchanged. For each internal time, we have a factor. See, here we have 1 over 2 pi to the fourth. So this 2 pi to the fourth, we just cancel this 2 pi over 4 here. So that's what the student was saying. Since they are going to cancel each other, just forget about it. But Feynman was a lot of a theoretician, was also experimentalist. So he was very formal in some calculations. So let's respect it. So we do that, and then that's a important point. And integrate So you have to calculate an integral. Please do not give up now, okay? Because this integral, in fact, will be very easy to calculate because we have this delta function, okay? Just to remind you. Yes. Okay. This integral is simply f a. So it doesn't really matter what the function f is. So even if you have a very complicated, that kind of integral that it makes you give up physics, okay? But if the fx is very complicated, it doesn't matter, because since you are integrating and this function fx is multiplying delta function, then this whole integral is just the value of that function at x equal to a. So, and that's what we're going to have here, because we have this delta function. Okay, so no matter what shows inside of the integral, the solution is easy. You just get fx, whatever it is, and replace x equal to a, and then that's it. So the integral is not really a problem for us to make. Now we have number 6, one by one. At the end of all this process, we have it'll be a delta function at the end of this. We'll see when we make the calculation. Okay? This delta function here conservation. Okay, so this is the momentum P1, P2, P3 to Pn. At the momentum of the particles that get into the process, those that leave in the process. All the energy momentum must be conserved for the whole process. So at the end, we have an integral, the result that shows this delta function that guarantees. So all we have to do is get rid of this term. So get rid of this term. Yeah. And the result is minus I m. Where? M is the amplitude. So at the end of all this mess, we end up with something that's minus I multiplied by m. M is what we wanted. Okay? So let's apply this to an example. Okay? For that, we'll close here and have another one. So let's apply this. That's the best way to understand how it happens, just doing. Like swimming. The best way to learn how to swim is throw someone in the swimming pool, and the person will swim or sink. Okay, like a computer a program to really learn how to write a program in Python, C++, whatever. The best way is just doing it. Okay, at the beginning it's complicated, but let's do some examples. Today is the 22nd, huh? 22nd September 2020. Lima, number 2. So let's do some example. So let's have fun now. And let's do something very simple, of course. Huh? Let's do a very simple, like to have this one A, go into B to C. Okay? That's one way to say it. Okay. If you have all these rules, let's follow all the rules. So we have to know the first rule, you must know what's getting into the system and goes out of the system. So what's the Feynman diagram? Let's write the Feynman diagram for this one. Okay, we have this Feynman diagram here, say B and C. It's raining a lot here, my goodness. Today is the first day of spring and it's really raining. Anyway, so this is the process we have. A, going to B and C. Fine? This is step one. Let's do step one. So, let's have here, let's say that here we have, say, P1. Okay? And this one will be P2. And here we have P3. Okay? In step one, that's what we have to do. We have to identify all the momentum for the parts that are into this process and the parts that leave in the process. And we also have to identify the internal momentum that we call Q1, Q2, and Q3. In this particular case, there's none. Okay? The A does not exchange anything. A is just going to B and C. So they're very simple. Okay? Now, what to do after that? We have to associate. If you took notes, I hope someone took notes, by the way. We have now to associate. Rule number one, we have to associate eta minus IG for each vertex. In this case, there is only one vertex, so it's very simple. And here we have P1, P2, P3. And then, here's one vertex we have minus IG here. This is the vertex, only one vertex. So there is only one vector, minus IG. Okay? Now, this process, the other step, means that we have to associate. Yeah? Associate. Factor. I, Q, J, square. That's what we have to do for each internal line. Again, there are no internal lines in this diagram, so there's no factor here. No internal. No internal line. No factor. Listen, we don't add a factor. It's not zero, okay? Since there is no factor here. Now, next step. Now, you have to guarantee the conservation of energy, remember? Energy and momentum. So it's step 4. So, step 2, 3, 2 pi, 4. In the case you have P1 minus P2 minus P3. See, since there is no internal line, then no internal momentum. Okay, so very simple. So let's put all this together. All this back together. Then, you put all this together, we have minus IG 2 pi to the 4. Now, 4 P1 minus P2 minus P3. Okay. Now, remember, there is no integral here to do, because the integral, we do the integrals. We do the integral over the internal momentum. Here, there is no internal momentum. So we end up with this expression here. Okay. Then, remember what we said? We just drop this term. Remember, we mentioned at the very end that at the end of all the operation, we're going to have a term like this, 2 pi to the 4th, and the delta function, we drop like this. Then the result is just minus IG. This is what is step 6. Then minus IM is equal to minus IG. So the amplitude of this process is M equal to G. So for this very process, Feynman diagram, we come that the amplitude M, we use this amplitude later to calculate cross-section, whatever we want to do. This amplitude is just equal to G. G is the coupling constant of this process, the intensity of this process. See? So it was very simple. Of course, this is a very simple model, but it did all the process. Now, let's know something a little bit more complicated, but not much more complicated. Remember that when we deal with the real particle, it will be more complicated because at some point you have to express the equations for an electron and the equations for a muon. And for that, we need some relativities, because those particles work, they are relativistic particles, so you need to describe them in a relativistic way. So we need some quantum mechanics for that. So we're going to have a very short presentation, maybe after tomorrow. So the way that we can get to what's called a Dirac equation. The Dirac equation allows us to describe an electron or a muon according to some equation that's going to use for this. And this will be a little bit complicated because, well, electrons, muons are more complicated than the particles A, B, and C that I'm just representing here. But this is, the toy model is very good for us to practice, at least to understand how to do things. So, other example, a little bit more complicated. This example here will be scattering. A plus A going to B plus B. It's a scattering. Okay? So, let's do the Feynman diagram. At least one Feynman diagram. And we say, you have A, here B, and B. Okay, let's see. Okay, remember that in principle, I have to write all Feynman diagrams, okay, for the process, and then add all the results. Okay, so here we have. Let's see what we do here. Let's say, okay, this will be my particle A. They are interacting here. This will be P1. Here will be P2. Here will be P3. and P4. Okay? The particle A, two particles A enter the system, and two particles B leave the system. In this case, they exchange something here. They exchange C. So the internal will be called Q. I'm not going to write Q1 because there is only one internal line. In this case here, notice, we have two vertices. Okay? So one vertex is going to have minus 1G, and the other vertex minus 1G. Okay? So we have one internal line. One internal line means that you have one propagator. So we have to add a factor that is okay. The particle in this propagator going between the two particles A is the particle C. So we have the mass of the particle C squared multiply C here is the speed of light. Later, I hope I can have the opportunity to show you that depending on the units that we're using, C will be equal to 1. Remember, the unit of a problem is something arbitrary. Okay, we're using meters, we can use inches, whatever. So, but in principle, that's have to be here the speed of light. So there's one propagator, only one propagator. And then we have two. Delta functions. One for each vertex. Remember that we also must assure the conservation of momentum and energy for each vertex. Okay? And the first example, there was only one vertex, so only one delta function. But here we have two vertex. And each vertex, no matter what the Feynman diagram is, each vertex must conserve energy and momentum. Okay? No exception. These are kind of sacred cows for us. So, what we're going to have here, uh, 2 pi four. So P1 minus P3 minus Q. Okay? This is the vertex, the first vertex here. Oh. Okay? You have P1 getting into the vertex, and you have P3 and Q leaving the vertex. So the ones that are leaving are negative. So you have P1 minus P3 minus Q. What this represents that P1, the delta function is 0 when P1 is equal to P3 plus Q. So conservation of momentum and the energy. In any other situation, this is 0. So the result is 0. This is one of them. And the other one is the other one would be P2. P2 is getting into the vertex plus Q. minus P3. Notice that the vertex 2, you have P2 and Q get into the vertex, and the P4 is one leaving. Then you have P2 plus P. No, there's not P4. Here should be P4. That's wrong. Okay? Now, what I said before is that we must have, you have one integration. Okay, I have to make an integration on this. And then, for the fun. Now, let's put all together. Then use the, let me see. Okay. Minus I, G. But we have it too, because you have two vertices. So each vertex has an IG. Minus IG. So minus IG is mine times minus IG. Here we have 2 pi. The 4. Integral. I T2. Minus MC. We want minus 1 on the other delta function, delta 4, P2, P2 plus Q. All of this integral is really not okay. Let's do that. I, G. Where am I? Where is fate? I. I put the two delta functions together, okay? Rather than having two delta functions, have just one delta function. So if I work with that, I'm going to have my I no I G square 2 pi 4. Okay. See, here we have something is here missing. The I here. So the minus IG, the I squared disappear, but you have another I in here. Okay. 2 pi to the 4th integral 1 q square minus mc square c2 delta function. Let's put them apart just to P1. My pencil is really not working well. P2 minus Q. I put them apart again just to make easy the calculation. P2 plus Q minus pi 4 P here. Here. So this is an easy integral because, as I said, this is an integral involving delta functions. And the result of this is minus I G square, okay, the 2 P 2 pi to the 4th, then 1 cells, why this is failing? P4 minus P2 square minus MC square C2 or P1 plus P2 minus P3 minus P4. No, so what happens here? To solve with the integral, we have to make Q must be equal to P4 minus P2. Okay, and that's the result. I got it. Remember, this is an integral of a function multiplied by a delta function. Okay, so the result is the original the function that will be multiplied when, in the case, Q is equal to P4 minus P2. That's what's here. And then Q is now P4 minus P2. Replace here. So this is the result we have. Then what we do, it happens the same as before. We have a term that's 2 pi to the 4th, and the delta function. We drop the term. We have. And we have minus I m is equal to minus G squared, P4 minus P2 square minus MC square C2. And then the amplitudes, that's what we want, M is just E square P4 minus P2 minus MC C. Okay, of course, in a real problem, this is the moment, the point when you have to write P4 and P2. That's what we're going to do with some example on the later. So in this case, the amplitude is very different from the first process. But wait. Do not give up yet. Wait. Now, this is the Feynman diagram that I show you was A, B, B. And he had P3, yeah, was P1, P2, P3, and P4. Okay. However, and here I have C. However, remember that all we see is in fact what's outside. And that means that it's also it's Feynman. It's possible that we have this A. Now the A. Here they exchange a C. So here we have P1. Here we have P2. Here we have Q. And here we have a B and a B. And here is P3. And here I have P4. No, it's not exactly the same thing, because here, whatever the values of the momentum, here what I have is the particle A at the bottom is the one that got the momentum P4. And the particle A at the top is the one that sent and up with the B with momentum P3. Now it's the other way around. So the particle A exchanged, the amount of exchange per C is different. So the small is not the same, this diagram not the same. So you must repeat this calculation for this diagram. Of course, we don't really have to repeat the whole calculation, because all we do is exchange P3 and P4. So in this case here, this is another first order. So in this case, the M would be P2, P3 minus P2 square minus MC square C2. So, as I mentioned before, the amplitude has to be this. You have to get all the Feynman diagrams for the process and then add up the results. So, in this case, then M is equal this is the answer. Okay? So, we made some calculation for a very simple, we call a toy model. That's not a real model. But we did everything that we are going to do when we have the real thing. Okay? In the case, we keep calling it G. The coupling constant will be G. And only at the very end, when we need something that will replace G, but it's real value. And then we have the momentum, or the momentum is still called the momentum P1, P2, P3, P4, whatever. And the mass will be either the mass of the photon, the exchange, and this will be 0, which simplifies a little bit the calculation, or the mass of the W and the Z, and so on. And then we're going to make the same kind of calculation for someone. Of course, there are other complications, because when you describe the momentum of the particle, the momentum has components X, Y, and Z. Yeah? For instance, when you have two particles interacting, say particle 1, particle 1 and particle 2, and they have the momentum, and they have the momentum. Okay, but when once they interact, they may end up going very different directions, as I mentioned yesterday. For instance, so if this happens to be the direction, say, let's say here is Z and here is X, for instance. So the momentum is going to have components in X and Z. The momentum component in X and component in Z, for instance. Okay? And of course, this will make the calculation a bit more complicated. But we're going to restrain our calculations, just to make it simple, to the case when they scatter, the particles scatter and come back in the same direction. So we'll not be concerned with component X and Y and Z, which makes our calculation a little bit simpler. Okay? Okay, I don't mean to say that this is very simple and that's obvious. This is clear, not obvious. Okay? What happens that the Feynman diagram is just a mnemonic. It's something that very intelligent people invented to get to an equation and then solve the equation. Of course, in principle, if you really know the theory, all the theoretical aspects very well, we can just get to the equation by a very complicated calculation. The Feynman diagrams help you to write the Feynman diagram, or all the Feynman diagrams that's possible, and then work through those Feynman diagrams, follow these rules. It's a lot of work, of course, but in principle, it's the kind of thing you can do step by step. And at the end, you get to a number if you don't make a mistake in a calculation. So it helps a lot to calculate. The Feynman diagram itself is not a theory. It's something very clever that was invented, and help us to take a picture of what's happening, what's the process involved, and from that picture, allow us, if you want, write equations, and then from the equations get the component that represented by each Feynman diagram. That's the amplitude. And then we're going to use that amplitude to calculate cross sections. When you get a full expression for a cross section, basically give us the information about the probability of some interaction to happen, something to happen. So as higher the cross section, means more likely that thing is going to happen. The smaller the cross section, less possible the thing happens. Also, be able to calculate. We're not going to do that, but in principle, we're able to calculate the lifetime of a particle, the decay of a particle. Because the decay, we also have a Feynman diagrams from the decay. I showed some Feynman diagrams yesterday for the decay of particles. So from that Feynman diagram, we can calculate the amplitude of each Feynman diagram from that decay, and then put that amplitude in an equation that will show the decay of the particle. Then we can calculate the lifetime of the particle, for instance. Okay? And people have done that. And people who did that And then when they compare the results they get with the results that are measured by experiments in labs, the results are amazingly well. Okay, so the theory works very, very well. Oh, my screen. Can you still hear me? Hello?
Yes, Professor.
Can you
Yes, hello.
still hear me? Oh, thanks.
No.
There was no, the connection today was okay, right?
Yeah.
Was okay. Oh,
We cannot see
okay.
anything from your iPad.
No, I know because I'm stopped sharing my screen. But if you want to see my screen, 3, 2, 1, 0. Okay, here's my screen. But I'm done for today. So that's the when I stop. Okay, I think we saw a lot today. Okay, what I want to see now is be a little bit of the quantum mechanics, a little bit of relativity, at least a little bit of quantum mechanics, so we can have the equations that we describe electrons and muons. And once we have that, we go to do the same thing now for the real thing, for the quantum electrodynamics. And so we can be able to solve, the solution for will be take much more than this, but exactly the same step. So maybe probably tomorrow, I plan on see a little bit of quantum mechanics. I believe that everybody has seen quantum mechanics. I'm just going to see a few details because the idea is to have the Dirac equation, okay? And the Dirac equation have a representation of electrons, I have a representation of all the other particles, and then we can solve the Feynman diagram. Okay, I will stop sharing my screen so you can see any other things. But I stop sharing, okay? And here you have myself back in my office.
Okay, Helio, many thanks. Oof, tired.
Okay. I think it was a little bit heavy today, but we have to go through that. There's no way to avoid this kind of thing.
Yes. Anyway, so
I also,
is there
I sent it to
what?
Professor Castromont a list of reference. Of course, I have not invented everything I present today. So you can see all this maybe with more details in several books.
Okay.
But do not get scared. Well, this is kind of thing that theoreticians love to do that. We just try to understand and see what to do. Okay?
Okay, Helio, many
So
thanks.
if you have questions, please send me email, and I
Yes.
try to answer all of them. Okay? See you tomorrow.
Okay, Helio. See you tomorrow. Many thanks. Okay, so guys, thank you for attending the mini course and see you tomorrow. Okay, take care. Bye, guys.